Nutrient film technique, or NFT, deserves a closer look because it's the backbone of commercial leafy green production worldwide. Walk into a hydroponic lettuce operation in Arizona, Canada, or Singapore, and you'll likely see rows of NFT channels stretching the length of the greenhouse. The design is elegant in its simplicity. Plants sit in small net pots or foam inserts placed at regular intervals along slope channels. These channels are typically made from PVC pipe or molded plastic. At the high end of each channel, nutrient solution is pumped in. Gravity pulls the solution down the slope, creating a thin film of water that flows past the root mass. At the low end, the solution drains back into a central reservoir, where it's filtered, reoxygenated, and pumped back to channels. The cycle is continuous. The key word here is film. The solution layer is typically only a few millimeters deep. It's not a flood. The roots are not submerged. Instead, they sit in a shallow stream of nutrient-rich water, with the upper portion of the root mass exposed to the humid air inside the channel. This provides the ideal combination: constant access to water and nutrients with excellent oxygenation. NFT works exceptionally well for fast-growing, shallow-rooted crops. Lettuce is the classic example. A lettuce plant in an NFT system can go from seed to harvest in 30 to 40 days, depending on variety and conditions. Basil, cilantro, arugula, pak choi, and other leafy greens also thrive. These crops have relatively small root systems and high water demand, which NFT delivers efficiently. But NFT has limitations. It's less suitable for large, heavy, or long-season crops. A tomato plant, for instance, develops a massive root system that can clog the channel. The plant itself can become top-heavy and difficult to support. Fruiting crops also require more space between plants, which reduces the efficiency advantage of NFT. The system is also vulnerable to disruption. Because the film of water is so thin, roots can dry out quickly if the pump fails or the flow stops. In a commercial operation, a backup pump and alarm system are standard. Even a brief interruption during a hot day can stress or kill plants. This makes NFT less forgiving than systems where roots are surrounded by moist growing media that provides a buffer. Another challenge is maintaining the correct slope. NFT channels must be level along their width but sloped along their length. Too much slope, and the solution flows too fast, giving roots less time to absorb nutrients. Too little slope, and the solution pools, creating low oxygen zones where roots can rot. Most systems use a slope of 1 to 2%, which translates to about 1 to 2 centimeters of drop per meter channel length. Channel length also matters. If the channel is too long, plants at the far end may receive nutrient solution that's been partially depleted by upstream plants. Commercial systems typically limit channel length to 10 to 15 meters and use multiple parallel channels fed from the same reservoir. Temperature control is critical in NFT. Because the film is thin and exposed, it warms up quickly under greenhouse conditions. If the solution temperature exceeds 22 degrees Celsius, dissolved oxygen drops and root disease becomes more likely. Many operations use insulated channels, chilled reservoirs, or evaporative cooling to manage temperature. Despite these challenges, NFT remains popular because of its efficiency. Water use is minimal. There's no growing medium to buy, replace, or dispose of. The system is easy to clean between crop cycles. And because the solution is recirculated, nutrient waste is low. Commercial lettuce farms using NFT can produce 15 to 20 harvests per year from the same infrastructure, with yields per square meter far exceeding what's possible in field production. NFT is a perfect example of how hydroponics trades simplicity for control. The system itself is simple, but managing it well requires attention to detail, monitoring, and responsiveness. When it's done right, the results are remarkable. Uniform, high-quality greens grown with a fraction of the water and land that conventional farming requires.